All right, let's start. Good afternoon. So first of all, again, a reminder for people that are taking the video streaming session, please send the proctor forms or let me know by email that you're planning to come for the exam in class. Okay, the first exam is October 10th. Okay, it's 1 week from Tuesday. Okay, and it's going to include everything from homework 1, homework 2, and the first project. Okay. All right. Have other questions about the project or the homework? There's something I want to address, but yes.
Yeah, and the project that asks us to apply the filters. Here if I pull it up. Yeah, it asks us to, in part 2B for the temporal derivative filter, try a simple 0.5 times minus 0.01 filter and 1
Yes.
Is that supposed to be applied in the temporal domain?
Yes. So let me, that's something I was planning to talk, so let me do it. All right, so the question was about the first project. So there has been confusion. So part A in the project, what it says is a listing of the kind of the software that you need to develop to do this project. And then part B says how to use that software. Okay, so part B1 says takes your image and apply a differentiation operator minus 1/2. Oh, 1/2 minus 101. And this is in the temporal direction. And the reason that we want to do this is because we're trying to find temporal changes. Okay? And we saw that to find changes, the derivative is a good idea. Okay? So in class, we developed this filter for finding changes in the 2D, in the spatial domain. Okay? In a single frame, we were looking for a boundary. Okay, now what we're looking is for changes in time. Okay, so I have my video. My video is made of many frames. Okay, so I have X, Y like this, and then I have time like that. Okay, and the idea is that you're going to do for every pixel in every frame, you're going to apply this filter in the temporal direction. Okay? Now, on the first frame, I'm having trouble, right? It's the same way that when we did in the spatial domain, if I wanted to apply a filter like that, in this guy, I have to do something about what happens here on the outside. Okay? So here what we're going to do is ignore. Okay, so before we said we could put a 0 over here, or we can replicate, or we can ignore, we can shrink. Okay, so what I apply a filter like this, it means that for the first frame I will not have an output. Right? The first frame I can have an output will be the second one. Right? So at this pixel location, what I'm going to do is apply this filter that has minus 1, 0, and 1. Okay, so it's doing the difference between the pixel in the same location on the following frame minus the value of the pixel in the same location in the previous frame. Okay, and what we're looking at is this pixel changing over time? Okay, and the reason that we're doing that is because if the camera is stationary and is looking at a stationary scene, that pixel does not change in time, right? This guy is always black. But today I'm dressed in black, so I'm not a very good example. But if I cross in front of something here that was white before, right? When I pass in front, that becomes black. So it has a change. Okay? And this filter is going to help me detect those changes. It's going to tell me when I'm crossing over in front of the white. Okay? Now, we saw that taking derivatives, which is what this filter is doing, is sensitive to noise. Right? So if my signal is noisy, when I do differences, the variance of the noise goes up. Okay? So we talk about cleaning the noise. So I also need to apply a smoothing filter in the same direction I'm applying this filter. Okay, so in the temporal direction, I'm going to apply a smoothing filter. Okay, now that smoothing filter could be a box filter, so it could have something that is like this, right? What this does is averages these 3 pixels over time. Okay, which is very similar to the first problem of the second homework. Okay, when you're estimating noise, what you're going to do is average all those images. Okay, so over here what you're doing is averaging. Okay. Now the project also asks to use a Gaussian filter. Okay, so that means it's a one-dimensional Gaussian filter. Okay. Now in class we saw that if I want to do a Gaussian filter, right, the equation for the Gaussian filter would be something of this form. K E minus 1/2 x squared over sigma squared. Right? Here I made it 1D. Okay? Yes? Okay. Now, how big my filter should be? How wide? It has to be an odd number. Well, let me put it again. It's convenient to be an odd number. We like odd numbers, yes. Now, we also saw something about the Gaussian filter. Do you remember? The symmetric, yes, but. So we saw that if you wanted this filter to really look like a Gaussian, and it has certain amount of the area underneath of the curve, right? I need to have a certain width. And the relationship that we saw is that a good rule of thumb is that the width of the filter should be 5 times sigma. Okay? Where sigma, again, is this parameter over here that has to do with the amount of smoothing I'm going to be doing. Okay? So let's say, for the sake of it, that I pick sigma equal 1. Okay? So that means that my filter has to have 5 elements in it. Okay? Now, what do I put here? I'm sorry? No. You're talking about how applying it, but I'm saying I'm building my filter. So what number does it go in my filter?
The Gaussian value of the pixel at that location 2 frames before.
Not the pixel location, not the value of the pixel. Yeah, I need to, this equation, I need to evaluate. What I want is to approximate a Gaussian. That's what I want. Okay? And I wanted to make as wide enough as over here is kind of small. You know, I really have a nice bell shape, not too much truncation at the ends. Of course, a Gaussian is infinite as support, okay? But I'm making it 5. All right? So over here, what I need to put is the value of this function evaluated at x equal minus 2. Okay? So I evaluate forget the k for now. Okay? I evaluate the exponential for minus 2, and I put it here. For minus 1, 0, 1, and 2. So it's symmetric, right? So because I have an x squared. This guy is the same as this guy is the same as this guy. Okay? Now these numbers should add to 1 because I want this to be an average filter. Okay? They're all positive, that's fine. But I also want them to sum to 1. Okay? So what I can do is divide by the sum of these numbers, and that will be my k. Okay? Now, I also typically want these numbers to be integers. Okay, it's nicer if they're integers. Okay, so what I can do is I take these numbers and divide by the smallest of all, right? Which will be the element here. And so make this guy equal to 1. Actually, it will be, yeah, this will be 1 because I divide by itself. This one will be something bigger than 1, right? But not necessarily integer. So I can round up or down, or just round, okay? Same thing here, right? And then I end up with some integer numbers over here. I sum those numbers, and that's what I put here. And that's my filter, okay? Again, I did this for sigma equal 1. If sigma was equal to 2, then my filter has to be at least 10, right? So I like odd, so we make it 11. Okay, and we do the same thing. Evaluate the function with the sigma equal 2 now, right? Make the smallest number equal to 1, round up to integers, and then normalize so the sum of the numbers is equal to 1. Okay? Yes? So now I know how to decide, and by the way, I think this is problem 2 or 3 in your homework. Okay? Now that I know how to design these filters, I have to apply these filters over here, okay, in my image. Now, say my filter has width 5, right? So that means that the first place I can put this filter is in the 3rd frame, right? So I will average with this weighted average, picks up in the first, second, 3rd frame, 4th frame, and 5th frame to give me one number, and I put that. So my video sequence is getting shorter. Okay, I'm losing the first few frames, and I will lose the last frames too. Okay? Is it more clear? Now the problem, the project is a little confusing in the sense that I also ask you to apply a 2D Gaussian filter at each frame. Okay, so this over here, what we're doing here is cleaning temporal data, right? So I'm looking along one pixel over time and see how it changes. And suppose again, if it was background, that pixel should not have changed, but it's going to have fluctuations because of the flickering of the lights. So we're going to average that using this Gaussian filter or your box filter. Okay. The other filter I'm talking about is like the one that we discussed earlier in the class. At each frame, you can clean noise by averaging with its neighbors. This is the assumption that each pixel is similar to its neighbors. Of course, that's not true when we cross edges, right? And the same thing here, the temporal thing, these pixels are not the same if something crosses in front, if there is motion, right? So there are places where that assumption that averaging will reduce the noise does not hold, but in general does. Okay? Is it more clear? Everybody? Okay. Yes?
Use the IM filter.
You can use the IM filter command, yes. Okay. Now, for the first problem of the second homework, right? The problem talks about the book Through Quanberry, which was a book that I used to use for this class. Unfortunately, it's out of print. That's why we don't ask it for anymore. But I have scanned the relevant page, and it's with the homework, so you can look at it. Okay, and the problem is very easy. What I want you to do is to generate an image that, if it didn't have any noise, is a very boring image. It's all gray. Every pixel, all pixels are the same. Every pixel is equal to 128. Okay, so 120. So you could generate an image in MATLAB very easy like that. Just say I equal 128 times once and n, where n is the size of your image, and you get a matrix is all full of 128s. Okay, that's my ideal image. Now what you're going to do is corrupt this image with noise. So you generate random Gaussian noise, uncorrelated, and you add it to it. It's additive. And so you get now a noisy image. And now you generate a new set of noise, and you add it to the clean one. So you generate like 10 or I forget how many I asked in the homework. You generate several images that they all ideally will be 128, but they all have different instances of Gaussian noise. And now, given that packet of images, I want you to clean it as much as possible. Right? That is to recover one image that ideally will be 128. Right? It's not going to be. Right? You will clean the noise, but to a certain extent, not totally gone. Okay. So that's that homework. Okay. Yes.
Are we allowed to use like built-in functions into MATLAB to like generate this noise? Or
Yes. 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 You can use run n, yeah, to generate a noise. Yes. Okay. All right. Any other questions? No. Okay. All right. So the plan for today is to finish talking about corners that we started on Tuesday, and then talk about scale invariant features like SIFT. SIFT is a nice feature, it's very popular, especially until deep learning. Right? After deep learning is less used, but it's a very useful feature because it doesn't depend on the viewpoint or the size of the image. We're going to talk about that today, and then we're going to talk again later when we talk about the stereo and how to do matching. We're going to revisit the SIFT feature. Okay, and then on Tuesday we will talk about the half transform, which can be used, for example, to find lines and circles and images. We will talk about RANSAC. And then on Thursday, the plan is, Friday, the plan is to have a review for the midterm. Okay. All right, so why corners are useful, okay, or why the SIFT features are also useful, which is some kind of corner. Okay, suppose I have an image like this, and I want a program to figure out of which city this picture is. Anybody recognize this city? It's New York City, yes. Okay, so here we have a picture that clearly is New York City, right? Here it has the Statue of Liberty. It has NYC there for more, if you are in doubt, right? But how do we know that this picture and this picture are representing the same city? Well, what we will do is to find features, okay, especially corners in this image and features in this image, and then we will try to match. Okay, and if we find enough correspondences, then we will say, I have found a match, and so this city must be New York City. Okay, this one had a label, this one didn't have a label, but they have enough features that have been matched that, yeah, I'm pretty sure that's New York City. Okay, here's another example. Say I have this pattern over here, I have this picture over here. I want to find that pattern in the picture, right? So I want to see that this is over there. So why corners is helpful, why I'm talking about corners for doing this task, might be better understood if we look at this cartoon example. Okay, suppose I have a patch like this. It's all black. Okay, and I have an image like this. It has all black and it has a red nice square on it. Okay, and I ask, where is this patch in this image? Can you really tell? No, there are many possible solutions to that, right? Because I don't have any distinctive features that will tell me where the patch is located on the image. Okay? So things that don't have texture, things that don't have edges, not a good idea. All right? Now, what if instead of having a black patch, I have an edge? Can you now tell me where that patch is on the image? I can tell easily where it's not, right? And all the places it's black. But then, and not on the horizontal lines, but it could be anywhere on these vertical edges of the square. Okay? So they have some information in terms of localization, but still I have too much degrees of freedom. Okay? On the other hand, if I give you this corner, clearly you can identify where that patch is on that image. Okay? So corners are useful. Okay? Anything that has texture in it will be useful because texture in some sense is a generalization of corners. Okay? All right. So we did this last class. I'm going to go quickly unless people have questions. We said that an oracle came and told me, build this 2x2 matrix, and you will be able to find corners by looking at this matrix and see if it's diagonal. And if the two elements of the diagonal are large enough, then we had a corner. Now we saw that if I rotate the corner and I build the C matrix, now I have trouble because any edge in any arbitrary orientation, not vertical or horizontal, will produce an image, a matrix that will not tell me whether I have a corner or not. Okay? So what we did was to solve the problem by reducing the problem to something that we knew how to solve, which is rotating the image. And the nice thing was that I didn't really need to find the rotation. I just needed to diagonalize this matrix. Okay? So if we diagonalize the matrix, and then I will look at the diagonal elements and see that both are large, then I have a corner. Okay? So that was the thing that we talked last time. And I started now showing the math of how somebody could actually figure out the algorithm, right? So I don't have an oracle that usually tells me things. So somebody had to sit down and think about how to design this algorithm. And this is how they came about, right? So the idea is that we're going to look at how much the intensity changes in a small neighborhood when I move around. Okay? So I have here the difference between the intensity value allocation x and y and a nearby pixel, which is just a translation from x and y by u and v. Okay, u and v is typically small. It's the size of a small neighborhood. It would be 3 by 3, 5 by 5, 7 by 7. Okay? All right, so I'm making a difference. And again, I don't care which one is higher or lower. So I'm going to do the square of that difference. And then I'm going to average in a small neighborhood. Okay, so I really want to see and smooth the noise of these things because these are noisy by just averaging. And we saw in class that we can choose different kind of averages. We can have a box filter average, or we can have a Gaussian filter average, for example. Okay, so this mask here, W, is doing that smoothing. Okay. Now, what we did was, last time, we wrote this term over here using Taylor's expansion. Okay, so we have a function of two variables. Okay, and I'm looking at the Taylor expansion around x, y. When I move a little bit, u in the direction of x and v in the direction of y. And so I have, to the first order approximation, these three terms. Okay, so we use this in the previous expression that we had here. I have dropped w for simplicity, right? And so what we saw is that when I expand this using Taylor, this term over here cancels with this term, right? And so what I end up having is just this quadratic form over here. And what we saw is that we could write this quadratic form using the matrix notation. And we got something that looked like that. Okay? And the cool thing was that this matrix over here is exactly the matrix that my oracle had told me. Okay? Yes? All right. All right. So how is this matrix now, how this form over here, it's a quadratic form, helps me finding corners? Well, first of all, let me put back the window. So the window, the only thing it does is multiplies this matrix in the middle. So I have the window over here. So again, if it's a box filter, this is 1. If it's not, it's a Gaussian. Okay. And now when we look at this, this is a second order polynomial. Okay, in two variables, u and v. Okay. And what it is the equation of an ellipse. All right? And the eigenvalues of the ellipse, of the matrix here corresponds to the size of the axis of my ellipse. And the eigenvectors corresponds to the orientation. Okay? And the ellipse itself, right, I can change by changing the this term over here. If I change for a different value, I will get bigger ellipses and smaller ellipses. So I have contours of these ellipses. Okay? So what this says is that by looking at the eigenvalues and the eigenvectors of this matrix that my friend in the Oracle had told me before and we derive now, I can tell whether I have a corner or not. Okay? And so we see that if both lambda 1 and lambda 2 are large, that means that I do have really strong edges in these perpendicular directions of the eigenvectors. Okay? Which means I do have a true corner. Okay? So if the eigenvalues are both large, I have a corner. Now, if one of them is large, but the other not, then my ellipse looks like very narrow, flat ellipse, right? And that has to do with an edge. Okay? If the other eigenvalue is much greater than the other, then I have an ellipse in the other direction. So that means an edge in the other direction. And if both of them are small, really what I'm having is something that's not changing very much. Not changing very much means no texture, it means no corner. Okay? Make sense? Okay? So here's a diagram again, lambda 1, lambda 2, and these are the regions on the plane lambda 1, lambda 2 that tells me whether I have corner, I have edge, or edge on the other direction, or I have a homogeneous region. Okay? Now, that required for me to find the eigenvalues of that matrix. Okay? Instead of doing that, I can do something else. I can compute this score. Okay? Let's call the score R, and it's computed by finding the determinant of the matrix and the trace of the matrix. Remember, this matrix is 2 by 2, so the determinant is cheap to find, and the trace is the sum of the diagonal elements, which is also cheap to find. Okay? Now, remember that the determinant is equal to the product of the eigenvalues, and the trace is equal to the sum of the eigenvalues. Okay? So this score over here, of course, has to do something with the size of these eigenvalues. And remember, I was using the size of the eigenvalues to determine whether I have a corner or not. Okay? So we can look at this R and try to see when that R will indicate that I have a corner or I don't have a corner. Maybe I can do this in a cheaper way than having to find the eigenvalues. Make sense? Yes? So what happens if both lambda 1 and lambda 2 are big? Which is corner, right? I know that there's a corner if lambda 1 and lambda 2 are large. What happened with this score? The product is going to be large, right? The sum is also going to be large, but the product in general will be larger than the sum. Yes? And also, I am multiplying the trace. I'm squaring the trace, so it's of the order of these guys. But also multiplying by k, where k is a small number. Okay? So when I subtract this from this, how is R going to be? Is it going to be positive or negative? Positive. And probably large, right? So it's a large positive number. Okay? Now, suppose both lambdas are small. What's going to happen? If both lambdas are small, this number is even smaller, right? And this guy over here is also small, right? And so I have a small number minus a small number. So I'm going to have a small number. I'm not sure about the sign, but it's going to be small. Okay? So no corner, like homogeneous. It will have some R number that's small, but I don't know the sign. Corner will have a large R, and it's going to be positive. What happens if only one lambda is large and the other is not? Which is an edge. How does the air look like? This guy will be not too large, right? Because I have a large number times a small number. So imagine that small number is very small, almost close to 0. So that's going to be small, right? And then I'm subtracting something over here that will be of the order of the large guy squared, right? So this might become negative, right? So this is the diagram that I had before in terms of lambda 1 and lambda 2, but now I have it also in terms of R. Okay? So for corners, what I expect is that this R coefficient is going to be large, positive number. Okay? For flat means no edge, so it's basically an homogeneous region. What I have is that the absolute value of R is going to be small. Again, it could be positive or negative, but small. And if I have R negative, then I have an edge, I don't know in which direction. Okay, because I have lost which lambda 1 and which one is lambda 2. But I know they're going to be negative. Okay? So here's an example. We're going to have a live demo in 1 minute, okay, where this was applied to this image. This is an image of some windows, and there are nice corners here, okay. So what you see over here is the result of the R score, okay, which was computed using a Sobel mask and a window Gaussian with sigma equal 1, okay. So you see that there are bright spots where the corners happen to be, okay. So these are the values of R that were less than a very large absolute value with a negative sign, okay? And so this corresponds to edges, right? We saw that R negative, right? It has an edge, so you see that it's picking up the horizontal and vertical edges of the window. If R is a large positive number, now I have these guys over here, which are around the corner locations, okay? And this something in between, which are neither edges or corners, all right? So the algorithm is very simple. We compute the image gradient, and we smooth it out. So we have here the x component of the gradient, okay, and the y component of the gradient is smoothed out with a Gaussian. Then we compute the squares of the both components and the cross product of the two components. Then we compute the sum of the products at each pixel using a window. So again, you can average with a Gaussian window or with a box window. So we get these averages images, and now for each pixel we can build a matrix that's given by these 4 components. It's a symmetric matrix. So I have the sum of the x squares, the sum of the y squares, and the sum of the products. Okay. We compute the response R by computing the determinant of the matrix minus k times the trace squared, and then we threshold R, and basically we're done. Okay. Now we are not quite done in the sense that I need to do this. If you see at the example I show you here, my corners are blotches. Right? I typically don't want a blotch. I want just a point. Okay, so what we do is very much like what we did with Canny, is we look at the point in that neighborhood that has the highest response, and that is our corner. Okay? Yes? Okay. So let me show you a live demo. Okay, so Okay. The first thing that this program is doing is finding that Gaussian filter is going to be used for convolutions. Okay, so this is an approximation of a 1D Gaussian with width 5. Okay, actually 7, from 0 to -3 to 3. Okay, so this is the field that is going to be used for smoothing. Okay. This was the image that was given as input where I want to find corners. Okay, and this is the output of the gradient of this image in the vertical and horizontal directions. So here you see edges, for example, for this square. Okay, let me try to make it wrong. One of them must be this one. Okay. All right. So this is the edge detection. So I have one component for the X and one component for the Y. So again, one point that's nice about this algorithm is that I'm going to build these C matrices by applying these operations in one shot to the whole image. And so I have the components for my C matrix for every pixel, computed for every pixel at the same time. Okay. So this is the X component. This is the Y component. Now, the next thing is to smooth them out. So this is the square versions of it and the cross product. So I don't know why it's getting so small. So this is the square of the Y, this is the square of the X, and this is the cross product. Okay, and after that we're going to smooth them out. And this is how they look like. Okay, so again I have ix squared, iy squared, ix, iy after being smoothed them out. Okay, and then now I am ready to assemble with these three images. At every pixel I can assemble a C matrix. Okay, and then I'm going to find the R-score by doing the determinant of the matrix and the trace of the matrix at every pixel. So now let's compute the R-score. And this is how it looks like. Okay, so you see that there are some bright spots where I was expecting corners. Okay, so let's threshold the R-score. And this is how it looks like. So now I see the places where the algorithm thinks there are corners. Okay, and then we can output them on the original image. At some point here it is. Okay, sorry. So you saw that it's finding corners where I would expect to have corners, right? The corners of the 3D shapes. It's also finding corners in places that, well, I'm surprised I got them there, right? But that's because there was some texture in the background and there's an edge of the circle and they meet together and they seem enough to a corner for the algorithm. So the point that I want to make is that this detector does find corners, but also find some things that you might have not thought about being corners to begin with, but on the other hand, they might be still useful for doing recognition and detection. Okay, there's just places where there is significant variation on the grayscales in more than one direction. Okay, so this corner detector is using that definition of corner. It's not the corner that you and I think about two lines crossing, but it's a place where the grade level values change in two different directions, more than one direction. Okay? All right. Now, let's talk about invariance. We saw when we started talking about this corner algorithm, right? I started with a corner that was along the edges of the boundaries of the image, of the pixel boundaries of the image, and then we rotated, and we saw that we could handle that, right? Just by looking at the eigenvalues. The whole point of making the matrix diagonal was to take care of that. So that means that if I rotate my image, I should still be able to find corners. You agree with me? So what that means in my parlance is that this algorithm is invariant to rotations, right? So if I rotate the image, I still get the same responses, the same places I would be picking as corners. And that's a good thing, right? Because if I wanted to match those two images of the New York City, they were not from the same viewpoint, so there was a rotation, right? So I want to be able to find the corners in both images at the same place. You agree with me? Okay. Now, on the other hand, this detector does not have a scale invariance. Okay? What do I mean by a scale invariant? Well, suppose that I have a corner like this, okay? And I'm using this neighborhood to decide whether it's a corner over there or not. So my algorithm will likely find that there is a corner there because I have grade level values changing in more than one direction. Okay? Now let's take that image and zoom in. Okay? So now I have this corner over here done like this. But let's use the same size of neighborhood I was using here. Okay? Now what happens when I move this neighborhood along that corner? Right? When I am here, I don't have two directions. I basically have one direction. When I have here, one direction. And here, one direction. So I will not detect this corner. Okay? So what this is saying is that my algorithm is nice that can handle rotations, but not so nice that it cannot handle zooming in my images. Okay? So I can change the viewpoint, but I cannot zoom in. All right? So here is an example. Okay? These are a lot of features that were found, okay, using that detector. Now I rotate, I basically find the same features. But if I change the scale by, for example, changing the size of the neighborhood I'm using, or zooming in or zooming out the image, then I get different features. Okay? And that's a problem, because when I want to do like matching the two pictures of New York City, I want to have the same features in both, so I can compare them. Okay? So if I have these two images at different scales, and in this image I find a feature over here, I really would like to find a feature over here, right? But my algorithm so far cannot guarantee that. It might be that I find it in one but not on the other. Okay? So how can I do this? How can I make sure that when I find features in one scale, I also find it in different scales? Okay, that's the problem of designing scale invariant features. All right? So let's look at how we do this. Okay? Let's go back to my example of the zoom-in corner. Okay? What we're going to do is we're going to evaluate some function at the place that we're dealing with. And we would like that function to be invariant to scaling. Okay? Obviously, the determinant of the, that neighborhood, of that matrix C in that neighborhood that we did, is not invariant to scaling. Right? If I change the size of the neighborhood, I will get a different matrix. I will have different eigenvalues. I might say, no, there's not a corner. So that's not it. Okay? But we would like to have something that is invariant. Okay? So what we're going to do is evaluate a function in different size of neighborhoods, right? And if that function is invariant at the scaling, what I would like is to identify that this scale is equivalent to this scale. Okay? And the way I'm going to do this, the trick is going to do is I'm going to look at this function when I have a local maximum. And the local maxima is what I'm hoping is scale invariant. Okay? So having a whole function that's invariant all the time is difficult, but maybe finding a function that the maximum of the function is invariant to the scale changes, that's easier. Okay? For example, what if I do the average of the grayscale values in the neighborhood? If I have the right neighborhood at the right scale, you would expect that the gray values in those two neighborhoods, when I change the scale, will not change. Make sense? Okay, so let's say I take a point in my image. I have two images, right? One at scale 1, another one at scale 2. So one might be a zoom version of the other. Okay? And I pick a point, and I pick at a neighborhood, and I compute the average intensity in that neighborhood. Okay? Now let's say that same point over here is here, but this image, actually this square corresponds to a much smaller square. Okay? Because this is zoom in of this one. Okay? So the gray level values here in this neighborhood should be the same as the gray level values over here. Right? So if I do the average over here and I do the average over here, they should be the same. But if I did this with a rectangle of the size of this, now I have many more stuff in this image that I shouldn't have. So the average in this square now is not going to be the same as the average in this square. Okay? So what I need to figure out is when the average here is equal to the average here. Okay? And that will tell me the right scale. Okay? So if I make a plot of the region size versus the grade level value average in that region, so I take this size and how much is the average, and I keep changing it until I hit a maximum. Okay? And then I do the same thing in the other image. Okay? The places where the maximums are, that is the scale that matches one with the other. Okay? So let's look at this example again. I hope this makes it more clear. So I have here, this is a zoom-in version of this guy, right? So I have a little neighborhood around here, which corresponds to this bigger neighborhood over here, right? You can see that like, the corner of my yellow rectangle touches the neck of this creature, okay? And here the corner of the rectangle is touching the neck of the creature, right? So you see that this square and this square are basically corresponding to each other, okay? So I would like to be able to figure out that this matches to that, okay? So what we will do is we take this guy and we compute the average intensity in that neighborhood, and we plot that as a function of the size of the neighborhood. So here I have one value, then I increase the size of the neighborhood, and I compute the intensity. Keep doing that, and I get this plot, okay? And this guy is maximum at this scale, okay? Now I do that same thing with the other image, plot, and the maximum is over here, okay? And that is when this guy has a corresponding patch to this guy. Okay, so what I'm saying is when this is maximum and this is maximum, I have the right size on here that corresponds to the right size there. Okay? Yes? So it solves the problem in a sense. That's the idea, the intuition, but it's still a little messy, don't you think? I mean, if I had to do this, right? So what we're going to do is clean this idea a little bit. But this is the intuition. The intuition is that I have some function that can tell me when I have matching scales in two images. Okay? When this neighborhood is equivalent to this neighborhood. Okay? All right. So for doing that, we're going to first introduce again our old friend, the Mexican hat. Okay? We saw this filter before. What was the use for it? Edge detection, right? And the Mexican hat is actually the Laplacian of the Gaussian. Okay? So it's a second order derivative of a Gaussian. All right? And we use it to find edges. And how were edges found using this filter? Where were the edges located? I'm sorry?
In the peaks?
No. Changing sign at zero crossings. Okay. The peaks is the first order derivative. The second order derivative is at zeros, but not just zero, but changing sign. So the zero crossings. Okay. Now here we're going to use it in a slightly different way, or a big different way. Okay. We're going to use it to find blobs. Okay. And so imagine I have these circles over here, and I have these different Mexican hats. What's the difference between these Mexican hats? Is the sigma, how much sigma is, right? And I claim that of these filters, the one that will have the strongest response to each of the circles is the one where it matches the size of the circle. Okay? So the smaller circle has a strongest response with the smallest of these filters. The middle one has a stronger response with the sort of the middle filter, and the largest one has a strongest response with this largest. Okay? So what I'm saying is I can use this filter to sort of figure out what is the scale of this blob, of this patch. Okay? So this is sort of my function I'm going to be using as invariance. All right? Now, let me try to show you that what I'm saying here is indeed true. I'm not lying, right? That when I apply this Laplacian of the Gaussian filter, I am actually somehow having strong responses with blobs that match the shape, the size matches sigma, which is the parameter of the filter. Okay? So let's look at that. Suppose I have a row in an image that has this profile. Okay, so it is black outside, and then jumps straight to white equal 1 in the middle, and the radius of this thing is 8. Okay, so that the width of that pulse is 16. Okay, do you understand what I'm talking about here? So think of a 2D image. I'm looking at one row of that image. I plot the grade level values, and this is what I see. Okay? So you can think of this white dot, okay, of radius 8, where I'm just looking at the diameter of that dot. All right? Okay. Now here, very faint, I hope you can see it, is my Laplacian of Gaussian in 1D. Okay? So it has this shape that it goes up, and down. Okay? So I'm going to apply this filter, and this filter has very narrow sigma to this image. Okay? And I claim that this is the output that when I do that. Does it make sense? Do you agree that that's a possible output of this filter applied to this signal? We say that find edges at zero crossings, right? How many edges I have here? 2, right? So you have 2 zero crossings. Yes? Okay, so here is one zero crossing, and here's the other zero crossing. Okay? So my response has a peak up, positive, when I'm encountering this edge, then dives down. I have the zero crossing for the edge, then becomes 0 because the signal is constant, right? And then again I have a zero crossing, and because over here I'm going from dark to bright, the zero crossing goes from positive to negative, but here I'm going from bright to dark, so the zero crossing will go in from negative to positive. Okay? So this is how the output looks like. All right? Okay. Now let's increase sigma. Make it bigger. Now you can see it better. Okay? And let's apply it again. Okay? And to the input. And that's what I get. Okay? Again, I have 2 zero crossings. But now what you see is that this interval over here is kind of smaller, right? What is happening? What's the interpretation? Why is this happening? Smoothing, right? I'm using, what is this? This is the Laplacian of the Gaussian. Remember what the Laplacian of the Gaussian was trying to do. It was doing a second order derivative, which is a zero crossing, okay? But also it was doing a smoothing. That's the Gaussian part of it, right? And I am increasing sigma, right? So it means more smoothing, right? And so what happens when I smooth these two things? What's going to happen to this pulse? It's becoming narrower and narrower, right? Because I am mixing more of the background with the foreground, okay? So this is what's starting happening here. These two edges are getting closer, and these two responses from this edge and this edge starts mixing up together, okay? Now let's increase sigma one more time, okay? And it's even more pronounced, the effect of the mixing of the two edges, right? Because I have more blurring. Okay. Now let's go to sigma equal 8. This is what I get. Okay. Let's keep increasing sigma. This is what I get. Okay. And you see that of all of this, the one that went all the way down, the streaming, okay, it was for sigma equal 8, which was the radius of this thing. Okay. So matching the scale, finding the scale where I have the maximum response matches the size of my pulse. Okay? So I can apply this sequence of filters at different scales and look when I have a maximum response. When I have a maximum response, I say that's the scale of the feature that I'm looking at. Okay? So here I have this beautiful picture of sunflowers with a lot of circles, right? Now what we see is that things that are far away are smaller. We know that, right? We spent a couple lectures talking about that. The perspective projection does that to you. Okay? So I have circles of all different sizes. I have big ones in the front and smaller ones in the back. Okay, so I apply a small Laplacian of Gaussian filter with a sigma small, and I get high detections, bright spots, at the places where I have small circles. If I increase sigma, now I start getting detections at bigger circles, bigger and bigger and bigger. Okay, so by changing the scale of the filter, I'm finding things that have different scale in my image, right? I'm finding the right scale for at each different location. All right? So what this means is that I shouldn't be just applying one filter. I'm going to apply a bunch of filters. And I'm going to see where these filters have a high response. Okay? And that tells me at what scale is happening. So if I have two sets of images of the same scene but at different scales, I can try to match where this set of images is maximum in this response with where this set of images is maximum in the response. Is it making more sense now? Okay. So what we do is, given an input image, we have the Laplacian of the Gaussian with different sigmas. And we have all of this together, okay? And so what we look at each pixel across the scales, and we find which scale gave me the maximum response, okay? And that tells me that at that pixel, the region of interest should be at that scale, okay? So I not only find that I have an interesting thing going on there, a corner or a blob, okay? But I also find the size of the blob at the same way, at the same time, okay? So now when I compare things, I can compare things at the same scale, okay? So here's the original image, and here is a representation of all those features found in just one single image. So I went from one to many, right? And now from this many, I can go back to one, okay? Each circle over here, what it means is that at the center of that circle, I have an interesting feature. And the size of the circle says the scale was important around that thing. Okay, so you can think of this is how big my neighbor has to be to say that there is a corner there or there's a feature of interest there. Okay. So now you can match features in terms of the space and scale. Okay. All right. So as you can imagine, this becomes a little more expensive than what we have been doing with the corner matrix, right? Because now I have to filter my image multiple times with multiple Laplacian or Gaussian filters, right? And not only that, we know that Laplacian of Gaussian involves second-order derivatives, right? And involves a Gaussian smoothing that we saw that to be good representative of the Gaussian, the width of the filter has to be 5 sigma. So the bigger sigma it is, the bigger my filter is. The bigger the filter is, the more expensive it is to pass it through the image. Okay? So computing these logs features at many scales becomes expensive. Okay? So one solution to try to reduce this computation time was introduced by David Lowe, which was actually the person that introduced the C feature that we're going to talk about in a few minutes. Okay, and his observation was that instead of having to compute the Laplacian of the Gaussian, he could have very similar profile of the function by doing the difference of two Gaussians. Okay, so here in blue, what you have is a one-dimensional Laplacian of the Gaussian for a given sigma. I think it's sigma 1 here. And the one in red is the difference of the Gaussian. And you see it's not the same clearly. There's a gap over here, there are gaps over there. But the behavior of this function as a first approximation is not too bad. Okay? So instead of having to apply these Laplacians, what we could do is smooth out with these Gaussians. Okay? So what we do is we smooth with Gaussian with a sigma equal to sigma, and we also smooth it out with a sigma k times that sigma. Okay? Why is that might be cheaper than doing this?
Like a lot less calculations, you don't have to take any derivatives or anything, just a difference?
Well, it's a difference between, you need to convolve first with this Gaussian and this Gaussian, right? So because the derivative, you will have to do the derivatives to make your filter, but once it's made your filter, you store it in your computer. You don't have to do it again and again and again, right? So that's not part of the cost. The cost is applying it. So why this might be cheaper to apply than this?
So like, when the expressions simplify easier.
Can you expand on that a little bit?
Like, the only difference is you're just multiplying k and sigma. So if you like write it out, you simplify.
Okay, so first of all, the Gaussian, we are going to decompose it in two 1D filters. Okay, so we can use the composition. But second, something that we talked earlier on is that applying the same Gaussian filter multiple times is equivalent to applying a Gaussian with a larger sigma. Okay, so instead of having larger and larger filters, what I do is I apply basically the same filter over and over. Okay, and I can have it. Okay, so here is how it looks like when you apply this difference. So I have an image that has been smoothed out with a sigma. I don't know what the sigma was used here. And the same image smoothed with a bigger sigma. Okay? And you can see this is blurrier than this, as you expect. Okay? Now when you do the difference between the two guys, this is the output. And what you see is that in a sense it's doing almost like an edge detection, right? Which is what the Laplacian of the Gaussian would be doing, right? We had edges where we have zero crossings. Same thing here. We have edges where I'm changing the gray values. Okay? So I'm going to talk about two ways of doing corners at multiple scales. They're very similar. They appear in the literature about the same time. One is based on the corner detector that we just talked in class, which is, by the way, if I didn't mention before, is the Harris corner detector. Okay, and the idea is we are going to find corners on the image and blurry versions of the image. Okay, so we take the image and we apply to it Laplacians different scales. Okay, and at each of these scales we find corners. Okay, and the places where we find a corner and at the scale that tells us it's an interesting point at that particular scale. Okay, so that's the Harris corner detector. And so this diagram, what it means is we have Harris corner applied at each level, and then we have different scales, and the scales are obtained by doing the Laplacian. Okay, now at the same time, David Lowe introduced SIFT. SIFT is more than just a corner detector. What it does is actually has a way of representing that corner, so it's useful for matching. We're going to talk about that later when we talk about stereo. But what he did was, instead of doing the Laplacian, what he did was use the difference of Gaussians. Okay, that's for scaling. But he also used the difference of Gaussians at each level. So he's finding edges at each scale. And the different scales are obtained by doing DOG. Okay? So here is how this is achieved. So we have our input image, and what we're going to do is build what's called a Gaussian pyramid. Okay? So what we're going to do is have the image, and then we're going to shrink the image, and shrink the image, and shrink the image. Okay? So that's the pyramid. How do we shrink? Well, we take a small neighborhood of the image and we average, and that we put it back in a single pixel in the next level. Okay. Now, that average could be box filter or it could be Gaussian, and that's what's doing here. So we're doing Gaussian averaging to go at each next level. Okay. So we have our original image, and we smooth it out with Gaussians of different sizes, okay? And then we reduce the dimensions by a factor of 2, and then we could do it one more time if we wanted, okay? So every image over here is a smooth version of the original image by a factor k more than the image below, okay? And then what you do is differences between consecutive levels, okay? So I take this level minus this level. That gives me a difference of a Gaussian. Then this level minus this level, that gives me a difference of Gaussian, and so forth. So I have now all the different scales. Okay? And then we apply our detector at each level. Okay? And of course, we can do this at each level of the pyramid. So I have a pyramid here, and I have a pyramid there. Okay? And now the result is that I have this image over here where at different scales, I have responses, and what I need to look is in which scale I have a maximum value. So the scale that I have the maximum value, that's the place where I say I have a feature, okay? And I also say the scale of the feature. All right? Questions? No? Yes?
Are we looking for the maximum feature because that will be like a corner or an edge? Or what are we looking for the maximum?
Is the maximum response, right? So we're looking for something that our detector is looking for. So in this case, we're looking for blobs, right? Because we're using difference of Gaussian as a surrogate for Laplacian of Gaussians, which I show you that fine kind of circles. Okay, so we're looking for dots in my image of different sizes. Okay, so I want something that have contrast around it, and it's almost like a dot. Yes.
How about this blob is not a circle, it's like what happened if this eclipse or something like that?
So yeah, so it will not be exactly like, but the response will be high. Yes, it's not an exact match, but you will find a high response in those places. Right? Okay. So how will you use now this scale features, scale invariant features to do matching? What would be the next step? Think of my first slide with the New York City problem. Like I wanted to match those two images. How will you do that? Sorry?
Okay.
So I'm locating my features. Okay. So let me go back to that slide. So I have these features, right? And hopefully now I have features over here too, right? Because I have worked so hard to have this detector that finds corners. So let's say, this the tip of this tower over here and the tip of that tower there is the same, right? So how would you use these features now to do the matching? It's something that we're going to talk later in the semester, but I want to. Yes?
The color between in the corner also.
The color. Okay, so yes, my mouse is on top of the top one, but this tip of the tower is kind of green, right? And that tip of the tower over there is kind of green. So probably those two features correspond to each other, right? So how do you think we can make that in an algorithm? How can I compare? What will you do?
Would you want to get like 2 points from each and then do like a coordinate transform, so like align the images the same way and then see if they match up?
That's your second project. We're going to do that.
Okay.
But for doing that, I first need to do the matching the features, because that will tell me how I can align. Okay. Average. What? So I could say, I could look at that neighborhood, right, and average the gray values around that neighborhood, right, and that give me a number, and then I have the averages in this neighborhood, and I know the size of the neighborhood, right, because I know the scale. Yes? And then I can say, is the average in here is equal to the average in there, right? So a first approximation, that is in the right direction. Okay. What we do in general is something like that, but instead of just looking at the average, what we do is this. So here I have the tower, and I'm looking at this neighborhood here, and here I have the same tower, and this is the corresponding neighborhood, right? So I have this found as a feature, this is found as a feature, And I have the size of the neighborhood here, and I have the size of the neighborhood there. Okay? So I'm saying, if this were to match, I still don't know if this is the same feature, but if they were to match, the whole patch around here in this size should match to the whole patch here in this size. Okay? So one thing we could do is do the average here of the grid values and the average here and see if this is the same. Okay? But that's just aggregating everything together. Okay? But what if this over here, I took this patch, right? And I try to match not just the average, but in some sense all the pixels here. And figure out a way of describing this patch and this patch in a way that will allow me the comparison. Okay? That's what the SIFT descriptor from David Lowe did. Okay? And basically what it did is find a histogram of the orientation of the edges in this patch and a histogram over here and compare that. So instead of comparing just the average, we have a little more information on how that patch looks like. Okay? But we're going to see that later when we talk about homography matching. Okay? All right. Now, let me introduce the next topic. No, that's an important thing. So the thing that the nice thing about SIFT is that it's not only a scale invariant, but it's also rotation invariant. Okay, to a certain extent. Okay, so if it changes too much the viewpoint, yes, it's not going to work. You're not going to have a good match. So in general, something between 35, 45 degrees difference of viewpoint, SIFT can handle. But more than that, then you cannot find it. Okay. All right. Okay. So let me talk about something that I was planning to talk actually on Tuesday, but I still have 15 more minutes. So let's say I have an image that has lines in it. Okay, so I have black background and white lines. And I ask you to tell me how many lines are in that image and where they are. Okay? So how will you do this? Based on all that we have seen so far. Find edges, okay? So I find my edges, say I apply Canny, okay? And so Canny gives me places where these edges are strong, right? So I will have high response on the lines, and low response where there's no line, right? Good step, okay? Now, going back to my question, how do I find the lines and how many lines are there? Direction of the edges, good. Good, okay, so you're saying that all of these edges over here, they have this same orientation of the gradient vector, right, which is perpendicular to the line, right? And so somehow we can aggregate them. Okay, cool. That's exactly what we're going to do. There's something called the half transform. And what it's going to do is going to count how many edges agree in an orientation. Okay? And if I have a lot of edges that agree on one orientation, I will say that all those edges belong to the same line. Okay? Now, just the orientation is not good, right? Because this line over here has the same orientation. So they are not on the same line, right? Okay. So let's start by talking in 2D, x, y. I have a line. What's the equation of the line on the plane? Let's say I use this equation. Okay? So what is the slope of the line? M, right? Okay, so all of the points on this line had to satisfy this equation, right? All of them agree that I have a slope M and an intercept N. Okay? So what we're going to do is we're going to count how many pixels in my image say that I have a line with slope M and slope N and intercept N. If I have more than, say, 10, I'm going to say I have that line that agrees with this equation. Okay? Yes? How do I do that voting? How would I do that? Say this guy has coordinates x1, y1. Okay? So I know that if this guy belongs to this line, it has to satisfy this equation, which means that y1 has to be equal to mx1 plus n. Okay? Of course, I don't know what m and n is because I don't know where the edge belongs to a line or not. Okay? So what I'm going to do is I'm going to consider all possible orientations and all possible intercepts and discretize them. Okay? And so I'm going to try for each of these points different lines. Okay? And see whether they verify the equation or not. If I have many points that verify the equation, I have the line. Okay? Now, let's pick another point here. And another point. And many points. Again, they all satisfy the same equation. Yes? Okay. So in these equations, what is the variable and what's the constant? X and Y are the variables. M and N are the constants. Okay? Now, I want you to switch your point of view for a minute and flip the order or the role of these two things. Okay? I want you to think about X and Y as constants and the M and N's as variables. Yes? So if I look at this in that way, okay, switch. Say M and N are variables and X and Y are constants. In the M-N space, if I draw a couple axes, M and N, right? Because I said M and N are now my variables, right? This equation where x1 and y1 are now constants. What does this represent? How do I draw this? How does it look like? A line, right? It's still linear. I'm just changing the role of things. Okay? Let's write it here. What I'm saying, I started with y1, or let's remove the index. I have y was equal to mx plus n, okay? So now what I'm going to say is n is equal to y minus mx, okay? And I'm saying now that the variables, actually, let me do it the other way, it looks nicer, minus xm plus y, okay? So now what I have is a line in the variables n and m where the slope is minus x and the intercept is y. Yes? So that means that for a point here, I can draw a line here, okay, in the Mn space. Now let's pick another point over here. That will give me another line, right? Let's draw it. Where do you think they intersect? At the Mn of that line, right? Because that's where they agree. Okay, so this guy has to be the Mn that I use here. Okay? Now let's pick another point. That gives me another line, right? That line needs to pass through that point. Okay? Yes? So, here's my proposed algorithm. I want to detect lines. Okay? So I'm going to do an edge detector. I have edges that are candidates to be in lines. That edge is a point. That point is a line here in what we call parameter space. I draw that. For every point that I get out of Canny, I draw lines. Now I look at this as if it was an image. Okay? And if I see a lot of lines intersecting in one point, that means that my points in the original image were all in a line. Okay? Yes? So what I did is I jumped from my image space to my parameter space. Every pixel in my image that was a candidate to be an edge gave me a line in parameter space. I make this image now, and I look. If I see this kind of a star pattern, that means that all of those points that created these lines, okay, had to agree in one single pair Mn. Yes?
How do we deal with noise?
Okay, so what will happen with noise is that these edges are not going to be really on the line. They will be close to, hopefully.
Several meeting points.
Right. So my thing will be not neat point. It will be a cloud, okay, where a lot of lines passes through. Okay, there are a lot of issues with this algorithm so far. I mean, it's not perfect. We're going to make it better. Okay, noise is one problem. Okay, there's a little more serious problem than that one. Anybody can think of any other problem that I have with this algorithm? What happened if my line over here was of this form? Where is the intercept? Infinity, right? What happens if I have a line of this form? Is that a problem? This one is not a problem, right? Because it has a slope 0, right, and intercept b. Okay? But here, what happened with the slope? Infinity, right? So I have a hard time mapping this. I said, let's look at this as an image. But now my image needs to be infinite big, right? Because the points will be intersecting far away. Okay? Any way I can fix this? Yeah, I could do that. I did that for the corners, didn't I? Yeah, but I'm not going to do that. I'm going to do something else. Another equation, good. Yeah, what another equation?
ax plus by.
Right. Okay, so this also is a equation of a line, right? And it's more general in the sense that this equation can handle these two type of equations, no problem, right? When I wrote this one over here, I assumed that the coefficient of y is not 0. Right? I cannot multiply by any number here which is not 0 that will make this guy 0. Okay? So this is a special equation. It has some biases, right? It handles this type of equation, but not this type of equation. Right? Because this one assumes that the coefficient of y is 1. This one has y coefficient 0. Okay? So we're going to use this. Okay? Let me make it a little more specific. This equation, if I multiply it by any constant that is not 0, gives me the same line. Okay? So if I want to go to parameter space with this line, right? First of all, I have 3 parameters, a, b, and c. Right? Before I had only m and n. Now I have 3. Right? I can go back to 2 by taking into account this scaling factor. Right? I can normalize this line in a way that I don't need 3 parameters, I only need 2. Okay? And one way to do that is by using the normal equation of the line, where if this is the line I want to represent, what I'm going to consider is the normal from the origin to the line. Okay? I'm going to measure how far that is. I'm going to call that rho. And the orientation of the normal, I'm going to call that theta. Okay? And I'm going to write the equation of the line as rho is equal to x cosine theta plus y sine theta. Okay? What I'm saying is this equation and this equation are the same, where I have picked a particular constant k. What is the constant k I picked? No, c ended up being rho, minus rho actually. This is a new A, right? This is KA, yes? And this is KB, right? Now look at the relationship between KA and KB. They are not just anything, right? What happens if I square them up and sum them up? I get 1, right? So I'm dividing by the norm of the vector AB, okay? What this is equivalent is to thinking about this normal. I'm using the normal of length 1, and therefore this is actually the distance rho. Okay, that's what's rho. Okay, so we're going to use this equation to represent the line. Okay, so now given a point in the image that's a candidate to be part of a line, that point is going to vote for a pair rho theta, which are now the parameters of my line. Okay, so instead of having m and n, slope and intercept, what I have is distance to the origin and the orientation of the normal. Okay? This representation solves my problem of an infinite range for m and n. What's the range of theta? Is it infinite? No. I could do it 0 to pi, or depending on conventions, I could do it between minus 90 and 90. Okay. How about rho? How big can rho be? Sorry, it's not infinite. Okay, in abstract, yes, it's infinite, but for images, the diagonal of my image, right? Let's put the origin in one corner, right? And I move the line. And how far can I move it? Well, until I reach the other corner. Okay? So rho and theta have finite domains. Okay? So that's good news, right? I can now represent my parameter space as a finite place, where here I have how much theta varies, and over here I have how much rho varies. Okay? Every pixel that is an edge is going to vote for a rho and theta. Okay? Now what we're going to do, and we're going to do it when we come back after the weekend, is we're going to vote, but not in the continuous space. We're going to vote in a discrete space. So this is really an image. Okay? And so whenever I vote for a particular rho and a particular theta, I add 1 to this pixel location. And now you're seeing this is forming like an image. And where I have many lines agreeing with, I'm going to have a bright spot over here. Except that this spot is not the intersection of lines. It's the intersection of something else. So think about that, and we'll talk about that on Tuesday. Okay. Okay. Thank you.